Devin Guan, the CTO of Drawbridge, and I want to introduce to you some of the problems that we are solving in Drawbridge. So since the introduction of... Oh, can you hear me? Oh, okay. So I have a soft voice, probably I should stand closer. So since the introduction of the first smartphone about a decade ago, there's been a proliferation of smart devices. This is like a global phenomenon. It's not only happened in North America and Europe, but it's also happened in Asia and every corner of the world as well. And by some industrial research, we are going to see about 3.6 billion smart devices, mobile devices, by the end of this year. And this is only counting like mobile devices. We are not talking about the more Internet of Things, smart appliances like Nest. And with that, we're going to have 3.2 billion Internet users by the end of this year as well, globally. So with this device proliferation, that comes a problem. Is the identity has been fragmented in the Internet world. So before this multi-device, before people have multiple devices, the marketers can reach the targeted audience through like the browser cookies, and online merchants can customize the online consumer experience by just leveraging the cookie sessions. But giving multiple devices, it's become a challenge to do it. There are, of course, companies in the world that can solve some of the problem for their own and operated websites, right? Name it Facebook, Google, Alibaba, Tencent. With their login and email registration handles, they can help their customers experience the same experience across multiple devices. But the online world is much bigger than this walled garden. Right? Think about all the your internet consumption on multiple devices. Like a big chunk of time is actually spent outside of these walled gardens. So that means we need a democratized solution to help everybody to understand this problem. So we have we have a debate when we introduce our solution to the world is a deterministic versus a probabilistic approach. The deterministic means that like people leveraging their registration information, email, name, like physical address to identify a user. Probabilistic means that we leverage technology, data, and data science to solve this problem. As I mentioned, because the massive scale online world, probabilistic is necessity in many cases. And also, as a data scientist, it's also much more interesting to solve it that way than like solving as a physicist. So how do we make this solution usable in the general industrial application than by just taking chances, right? Probabilistic, sometimes people take it as you're taking a chance of the data. We have to have a solution that can have enough precision and recall to satisfy the client's needs. A solution that can have enough precision, to target your user with confidence, and also enough scale to cover enough of the audience space. That means anyone think about this problem should have open access to the data. Data has to be portable, right? Both your data and your algorithm has to be portable to many use cases. And you have enough scale to solve to hit the critical mass for many users. And also, you have enough anonymization to protect user privacy. So where do we start? Like, we are living in a world that with massive amount of data, and how do we do it? We take an approach that leverages a unique industry that with significant amount of data that we can access. So we use the advertising as an industry to apply our algo for two reasons. One, advertising industry has significant amount of scale. We are talking about 70 to 100 billion requests a day. And you can reach hundreds of millions of users every day in advertising. Not only has enough scale, but it also have enough detail in the request. Like for each ad request from a device, we understand where the user is making the request, what device they're making the request, when they make the request, and what context they make the request. Like for example, what app and what website they're using. So that makes applying our algo, it's very possible, and there's enough information for us to make a really interesting algorithm out of it. So in Drawbridge, we are taking approach of like solving this problem, but this is we are in such an early stage of understanding this framework and the problem, and we want to draw on the industry and the community's smart and creativity to solve this problem. Next, I want to introduce our senior data scientist to go into how one of the approach that we solve this problem. Randy?
Cool, thanks, Devin. Yeah, so I'll talk about the art and science of how we create digital identity at Drawbridge. And the first thing I just want to say is that I'm not the only artist in the colony. So we have Shang and Mingyang are also here, and they can probably talk more candidly than I can offline. So if you're interested in what we're doing, please find them. So I want to reiterate one thing that Devin just said, which is that this is as much an art as it is a science. So the vision is very ambitious, obviously, to be able to make a huge amount of anonymous identities of high quality. It's also a brand new problem. So the world has never had this problem of device proliferation before. And it's also a problem that needs to be solved with technology that only existed for the last few years. So I just want to reiterate that there's plenty of room for creativity, even room for papers to be written, if that floats your boat. And hopefully something in this talk will connect with what you're doing. So since this is KDD, my version of the talk will be a little bit closer to research and talk a little bit about the things that we've done and the concepts that we've been interested in that had to do with very active areas of research. So Devin talked a lot about identity and a lot about ad tech data and didn't say much about graphs. The title of my talk has to do with model building on graphs. So what graph am I talking about? Well, so for our team, the main deliverable that we have to come up with is this black box that turns a messy world of data into this very manicured world of anonymous identities, which are basically represented by bags of devices that they probably own with high probability. And all that messy data naturally comes in the form of graphs. So we have a handful or a couple handfuls of different namespaces like IP addresses, device identifiers, apps, visited URLs, geolocations, things like that. And these things are all generically related to each other in many-to-many mappings. So this sort of screams, I'm a graph, think of me as a graph. The other thing about our graph is that it's passively collected in ad tech data. So it's only approximately or incompletely observed at any given time. As time goes on, it evolves. So we have like this time series of massive graphs. And then it's also very noisy. So your phone is not owned by all the people who were in line with you at the cafe this morning, But as we open up our data for the first time, it might appear that way to us. And so what we're trying to do is to actually generate yet another graph. So the graph that we're trying to generate can answer a question like this. So which sets of devices are probably owned by the same person? So not that they're owned by Randy, but that they're owned by some person. And in order to do that really well, we have to do these two things really well, which is we need to know how to build machine learning models on graph structured input. So that means machine learning models that really know about the graphiness of the data they're looking at. And then two, since we won't be able to do one perfectly, we need to be able to run graph algorithms like community detection on top of these outputs. And we need those algorithms to be extremely scalable, so we can do them on 10 billion nodes, and also extremely intelligent so that they don't ruin the hard work that we did in the first part. So it turns out to be easy to do either one of those things, have a super scalable community detection algorithm or a super smart community detection algorithm, but it's actually hard to do both at once. So we'll go into some of the tricks that we found useful to try to accomplish that. So to go into model building on graphs, let's look at our sort of bread and butter classifier. So this is the thing that scores the likelihood that two devices are owned by the same person. So for this, the sort of old school way to do this was to have some sort of count of co-occurrence, say like IP co-occurrence, and then you would TF-IDF the data, and then you'd automatically have a score that told you somehow these devices think that each other are important. So that worked maybe 5 years ago, but now obviously what we want to do is train a supervised model with as much context shoved into it as possible. Okay, so for that model, I can't talk a whole lot about the feature vectors, but this thing on the left is a little cartoon of the different chunks of our feature vector. So obviously you want to include some information about the cookie and device in their own right, general activity levels, demographic estimations, things like that. And then there's this big set of features which have to do with the context in which they were seen together. But the class that I want to focus more on is this part D, which is facts about other neighboring pairs. So they have less to do with this pair and more to do with nearby pairs in our graph. So why would those kind of features be important? So here's an example on the right. Imagine that we're trying to score this pink dashed link between these two devices. This may be the first time we've ever seen these devices co-occur together. So we won't be able to make a really strong statement about they're probably owned by the same person. Nevertheless, we don't want to wait. We want to make the best estimation we can as soon as possible. So you can imagine that it would be good if you saw, in addition to these purple feature vectors, also this whole picture of the graph, so that you could see that there was already sort of two strong paths between these two devices, and that maybe you should adjust your expectation and say, yeah, these are possibly owned by the same person, or vice versa if you see the opposite. So as a data scientist, I can sit around all day generating features that I think are important about the graph, but what we really want is a systematic way of knowing that our models have seen everything about the graph that is useful to them. And for that, we turn to this sort of burgeoning literature on graph representations. So how do you show a graph to a machine learning model? So there's sort of two banners here, which is the prescribed representations and the learned representations. So the prescribed representations have sort of been ironed out in the last 7, 8 years, and the learned representations are really new, sort of the last 18 months. So for the prescribed representations, that's usually things like graphlets, like a basis of shapes of graphs, or a way of describing the graph in terms of random walks or shortest paths. Or also like this example I'm showing here, which is Weisweiler-Lehmann. So the idea of this is that you can very efficiently start with any graph that has discrete node labels on it. So, I mean, for the purpose of our discussion, those labels could be device types. So these labels could be like iPad, Android phone, PC, something like that. So we start with a graph that's labeled with those guys, and then the graph queries its neighbors. Each node queries its neighbors and makes this short string of sorted neighbors labels, and then hashes that and creates new labels. So we have the second version of the graph which has new labels on it. And those labels are more specific than the first label. So instead of saying I'm an iPhone, it's saying I'm an iPhone that's next to a PC and an Android tablet. So the feature vector is just counts of these different labels. And you can see you can keep iterating this, but every time you iterate, the counts get larger and more sparse and more specific. So this has been really interesting for us because it's very efficient to calculate and turns out to produce some good features. So in the second class of things, in these learned representations, the biggest through line in the literature so far has been turning skipgrams onto graphs. So if you know about word2vec, you've probably used skipgrams. Basically, the idea there is, words generate a sentence, and you should show this neural network one word and then have it predict the words that might be next to it in a sentence. If you want to apply that to graphs, then what you're thinking about is these substructures in the graph form a graph in the same way that words form a sentence. It's just some weird, funky graph language. So then the question is, what's the context for a substructure in a graph? And basically, that's how the different papers differ here. So you can read these papers. There's subgraph2vec, deep graph kernels, node2vec, which is actually presented in this KDD. And they basically all have different ways of coming up with this context. So here, subgraph2vec is using a radial context. So they say, around this starred node, you can look at BFS searches to various step sizes. So the context for the BFS at 1 step is the BFS at 0 step and the BFS at 2 steps. So if you show that to your neural network, you train the skipgram model, then you'll have vectors. And it's really cool. These guys actually showed, you can ask semantic analogies just like in word2vec. So you can say, what's similar to a box in the same way that a triangle with a tail is similar to a triangle. And you'll get box with a triangle automatically. So it's really cool. And exciting for us, we've just started messing with it, but exciting in that there are already tools like GenSim that are very parallelizable. So definitely an interesting piece of technology. And then there's this cute statement that we have scored pairs and we make a graph with them. And then we have graph-based features, so we featurize that graph to make a better scored pairs. The better scored pairs make a better graph. And on and on. So you can continue that process if you want to make sure that you squeeze the most juice out of this. So that's a bit about machine learning on graphs. The second part of this is about where are the actual identities in this graph. And for that, we talk about community detection. So if we had done the pair scoring perfectly, then we would just run connected components on the graph and all the user identities would fall out. But obviously, we're not there. So what we have are clusters that look more like this. Some of them you could say, yeah, maybe that's one person. Some of them I would want to take a scalpel to and break it into 2 or 3 people. But basically, even if with a moderate score cut, the entire graph looks like any complex network that you've read about before. So it has power law degree distribution. It has a giant component. So something has to be done on top of that. So we're talking about community detection at massive scale. Maybe one thing that can be said about this is it's kind of like supervised clustering in that we have some deterministic labeled edges. So we can define a precision and a recall at cluster level. And if we have some algorithm that's driven by a fitness function with parameters in it, we can move those parameters around and measure the overall precision and recall of that algorithm. But the thing that's really tough about this is that when you get to extreme scale community detection, the number of algorithms you can use is really small. So it falls into this greedy algorithm category. So it's like label propagation, fast unfolding, things like that. The things that we'd really like to use is something like simulated annealing that would give us higher quality clusterings, but they're simply too expensive at this scale. Unfortunately, greedy algorithms also have this problem that's well studied, or several problems, but the main one for us is the instability to the input. So what you find is that the fitness function over the set of all clusterings has this exponential number of things with very close fitness. And those things actually macroscopically don't even look the same. So if I run my algorithm twice on slightly different inputs, I'll get a completely different looking graph because this greedy optimizer is not super strong. So that's a big problem, and how do we get around that? So a couple of things that we've found to be useful to get around that problem is, first of all, consensus clustering. So that looks like bagging in the unsupervised learning context. So just come up with some ensemble of clusters, have some consensus function that averages them into one final clustering. So that is really interesting and can sort of help on both the quality and the stability fronts. Secondly is link prediction. So since we have these deterministic handles that are attached to IDs in our system, we don't even have to have seen two IDs co-occur before to consider whether or not they're a true pair. So for this dashed line here, we can still go ahead and label it as plus or minus 1 and build a link prediction model on top of that. So that's good because we add extra edges that have been trained by a legit supervised learning algorithm into our graph pre-clustering. It's also good because it's a temporal predictor. So if this thing says, this link that you've never seen is really likely to exist, then it's also saying you're likely to see it soon. So that sort of builds in like a future version of the graph into the current version of the graph. And sort of the last thing is just this actually old idea from 2006, evolutionary clustering. So the idea there is you just take your fitness function and subtract a penalty term, which is penalizing a difference in the graph between two versions. So this is sort of heavy-handed. You trade off some precision when you do it. But the trick is if you trade off a little precision for a lot of stability, then you've probably done all right for yourself. So that's all I wanted to say about that stuff. Hopefully it opened up the black box a little bit. The idea is just when you serve this hot mess of ad tech data into this black box and you want to get a billion quality users out of it, you have to push yourself to some tricky ideas in machine learning. So with that, I will give you back to Devin.
So as Randy mentioned that we are solving a problem at a massive scale. At Drawbridge, we were able to connect 1.6 billion users across the entire world. And it's spread into multiple continents. And all these billions of users actually can break it down, consist of many, many more connected devices. So what are we trying to solve in this world? We want to provide a solution that can help provide a online, a safe, and personalized experience for our consumers. So, so that like when you go to a site that outside of those walled gardens, you can have like very consistent and safe experience across multiple devices. And imagine that like what this a solution like this can provide for the world, right? And as Randy mentioned, we see this problem fits very well into a graph learning, structure data with the machine learning techniques. So we want to call on people that have the interest in this area to like join us and solve this problem. Obviously, this solving a fragmented identity problem is much bigger than Drawbridge itself, right? It's just like how recommendation engines are bigger than like Netflix, right? So we should have like draw into the community's talent to help us to solve this problem. That's it. So the question was like, how do we get access to the data and what's the data source? So we leverage our advertising engine to ingest like 60 to 70 billion requests a day, and with about hundreds of millions of IDs into our system. So that's a huge amount of data. Like when Randy talked about our graph structure, we're talking about tens of billions of edges and billions of nodes.
Any other questions? Cool. If not, let's thank Devin and Randell.